So in the previous video, we addressed a particular function where we were looking at the limit, and from the left side it was going to one place, but from the right side it was going to another place. And we said that means that the limit doesn't exist. If it's not going to the same place from both directions, the limit doesn't exist. However, as I kind of previewed, we can evaluate limits from just one side. And this is really about building that notation as I'm approaching values from the left. And keep in mind that that means that I'm going from left to right. So if I'm approaching a particular value, so for example, here in a moment, we're going to find the limit as x approaches 3. Well, that means I'm approaching from the left. That means I'm approaching values less than 3. What the notation looks like, and I'm going to go back to kind of our generic notation where we talk about the limit as x approaches c of f of x. But if I'm addressing it from the left, I note that with a little minus superscript right there above the c. And that tells people you're looking at it just from one direction. So we'll talk about the limit as x approaches c from the left. That little minus sign notes that. It kind of follows pretty intuitively then that if I talk about limits from the right, so again, if I'm approaching 3, but I'm approaching from values greater than 3, then what I'm looking at is the limit as x approaches c from above, which is noted with this little plus sign, the limit as x approaches c from above of f of x. And a lot of times you'll hear people say from the left or from the right. You heard me just say, you'll also hear people say from below or from above. Those are all synonymous, meaning the same idea, that you're looking at it just from one particular side. Now then, in order for the limit to exist, these one-sided limits have to match, and that's what we saw in that previous function. So we can say if the limit as x approaches c from below, or from the left of our function f of x, equals some value L, and that also happens to equal the limit as x approaches c from above of f of x. In other words, if the two limits match and we're going to the same place from both directions, then that's when we can say the limit as x approaches c, no longer talking about it from one side, just the limit exists and is equal to L. And we should note again, this is where L is a finite number. In order for the limit to exist, it has to be approaching a finite value. We'll actually talk about when it's not approaching a finite value in the next video. But let's just take a look at this graph that we have here. And we're going to take a look at 3 particular points. And we're going to talk about the one-sided limits and what that means for the limit overall. We're going to look at what's happening at x equals -4. And then we're going to take a look at what happens for x equal to 3. And we're also going to take a look at what happens for x equal to -1. So let's start off where x is equal to -4. The first thing I want to note, we're going to talk about limits, but I also want to make sure that we know what is the function value at -4. And remember, this particular value right here, f of -4, is going to have nothing to do with the limit, but I think it's worth noting, especially when we start talking about a particular topic later on in this unit. F of -4, I have a value at -4, my function is equal to 3. That's a true statement. That point exists on my graph. Now I want to talk about what is the limit as x approaches -4 from below of f of x. Well, that means that as I'm tracing over my function, as I'm approaching -4 from the left, my graph is still approaching 3, and so it equals 3. I then want to take a look at the limit as x approaches -4 from above of f of x. And so now I'm approaching -4, but I'm approaching it from the right here. And you can see my function once again, or my limit, is in fact approaching the value of 3. And because these one-sided limits match what we just defined here, we can say that means the limit as x approaches -4 of f of x exists and is equal to 3. And this actually means something really important in terms of what's happening to this function at this point. And we'll talk about that much later here in Unit 1. Where things start to get really interesting is when we start talking about what's happening at x equals 3. So if you take a look at x equals 3, that's where I have this little hole, and then this gets filled in here. So let's make sure we understand what's happening all over the place with this graph here. I know that f of 3, in other words, the function value at 3, is this point down here at -5. So I can say f of 3 equals -5. However, when we start talking about the limit behavior as x approaches 3, we'll start off from below of f of x. So in other words, as I'm approaching 3, if I'm tracing over my function, and remember with limits from the previous topic, we don't care about what actually happens at x equals 3. We're just taking a look at what happens as I approach 3, and in this case, as I approach 3 from the left, and you can see based on where my hole is, the function is approaching the value 5, and so that's the limit as x approaches 3 from below is +5. I can say the limit as x approaches 3 from above of f of x. So now I'm approaching 3 from values to the right of 3, and you can see that again my function is approaching the value +5. And once again, not even considering what's happening at f of 3, the fact that the one-sided limits match means that the limit as x approaches 3 of my function f of x is equal to 5. Now then, f of 3 does not equal to 5, but the limit as x approaches 3 does equal to 5. And this particular column looks something very similar to what we were starting to address in topic 1.2. Where things get kind of tangly here in terms of at least the one-sided limits is whenever we have this jump at x equals -1. So let's get the notation down to describe what's happening at -1. Well, first of all, f of -1. The function value at -1. Where is the point at -1? Well, the closed-in point is at -2. Where things get interesting is when we start talking about the one-sided limits. The limit as x approaches -1 from below of f of x. So in other words, if I'm tracing over my function, as I approach -1 from this direction from the left, you can see my values are approaching 1. However, whenever I approach from the opposite direction and look at the limit as x approaches -1 from above, so now I'm tracing from this direction headed to -1, you can see my function values are approaching -2. And the fact that these one-sided limits don't match automatically means the limit as x approaches -1 of this function does not exist. So remember with limits, we don't care about what happens at the actual value. So for example, at x equals 3, yeah, we had the point 3 -5, but it had no bearing on the actual limit. And then the big thing to take away from this particular lesson is that if the one-sided limits don't match, and you can see that's what was happening at -1, we were going to different places from different directions, that's what makes this limit as x approaches -1 of f of x where it does not exist.